Yo, welcome in your maths, and I got a new video on this video series, and in the previous video we have discussed this and more about the history and transformation of this name. So now let's move to the part 7. So in this video we will discuss irrationality from continuous fraction. That is, we will going to be measure the degree of irrationality. Now let's understand the first point, that all rational number can't be expressed as a simple continued fraction according to the Euclidean algorithm. Now what is continued fraction? So first of all, let's understand the second point. But all irrational number can be expressed as the simple continued fraction according to Euclidean algorithm. Now what are these all things? Let me explain with examples. So let's say we have the example that is 1, which is a rational number which can be written as 1 divided by 2 minus 1. And now this 1 here can be substituted as this value of 1. Okay, so we can write this one as 1 is equals to 1 upon 2 minus 1 by 2 minus, then 1 can be substituted again, 1 divided by 2 minus 1, like that, because you substitute again and again the value of 1. So this is basically approaching to infinity. So the irrational number basically approaching expressed as a simple infinity continued fraction. Okay, and here you also have to write all rational number can't be expressed as simple infinitely continued fraction because it is according to the Euclidean algorithm. But here what I have written is not according to the Euclidean algorithm, and the simple means basically when the numerators are 1. Now like that, there is one more type of continued fraction, and that is finitely continued fraction, which is the opposite of infinitely. So the finite continued fraction is something look like, for example, 2 upon 3 minus 3 upon 2 minus 1 by 2. And for solving, you will have to go from the backward direction. Like this, you can solve from backward direction. But how can we solve this infinitely continued fraction? Infinite continued fraction. So we will discuss this later on the video, but there is one confusion, that all rational number can be expressed as simple infinitely continued fraction. Then why it is written can't? Because remember, it is not according to the Euclidean algorithm. So therefore, in the more formal term, it is not simple infinitely continued fraction. Okay. Now let's see what is Euclidean algorithm. So the first point is the integral part of a number. First of all, find out the integral part of the number and then find the fractional part of the number. Second point is reciprocal the fractional part and again find the 1 and 2. Okay, means again repeat the process. So now what is integral part and fractional part? So let's say we have a number here that is x. Okay, and let's say the another number here that is y. Okay, so now you have to go from right to left. Okay, so for the number x here, the starting integer will be called as the integral part of x, and this distance will be called as the fractional part of x, represented like this, and this represented like this, which is the integral part. And when you add these two, you get the number x. Similarly for the y, if you move right to left, this will be the integral part of y, which is represented like, this is y here, and this is the fractional part of y, and when you add these two, you get y. So now let's apply the Euclidean algorithm for the irrational number. Let's say we have root 2, so it will be 1.414. So here the integral part is 1 plus the fractional part is this one, so 0.414, and it is moving, okay, so on. So now we have found the integral and fractional part and written like this as well. So now the first step is completed. Now the second step is to reciprocal the fractional part. So this part we have to reciprocal it. So now this part we can also write it like this, root 2 minus 1. Okay, because you can see clearly that when you send the 1 to the LHS, then this is the value of 0.414. So you can write, now you have to reciprocal it, so you can reciprocal it like this. Okay, now let's find out the value of this denominator. So here it is 1 upon root 2 minus 1. When you multiply root 2 plus 1 in the numerator and denominator, you get root 2 plus 1 divided by a minus b, a plus b, that is a square minus b square, that is 1. And you can clearly see, you can write this 1 and this whole as this, which is root 2 plus 1. Now can you see that root 2 is 1.414 and plus 1, that is 2.414. Therefore integral part is 2 and 0.414 is the fractional part. So now can you see that 0.414 can be represented as like 1 upon root 2 plus 1, as you can see here. So I can write it as 1 upon root 2 plus 1, but root 2 plus 1 again can be substituted and made like this infinite continued fraction, simple infinite continued fraction, because the numerators are 1, and that is the thing we have not performed for the rational number. Therefore it cannot be represented as simple infinitely continued fraction according to the Euclidean algorithm. Now pi is also an irrational number, so therefore it can be also represented as simple infinitely continued fraction, as you can see, because there is 1 present. Okay, and all irrational number has 1 in the numerator, so this is also the simple infinitely continued fraction. Now let's see how to solve this. For solving any infinitely continued fraction, you first have to solve this part, and then you have to solve this part, and the more part you solve, you are getting much more closer towards the approximation of the irrational number. So now let's solve this part. So this is 3 plus 1 by 7, which is equals to 22 by 7, the basic approximation of the pi, which the value we will tell after solving other parts. Okay, so the next part, when you solve this part, let's say it will be 333 upon 106. When you solve, you will get this. So as you solve the other parts, you are getting more closer towards the value of pi. So now let's find these fractions value in decimal, and let's compare it with pi value. So the decimal expansion of 22 by 7 is 3.1428 and so on. So it will matches till 2 digits after decimal, and it will again stop because it is a rational number. So now let's move to the second part. When you solve till second part, then it will matches till 4 digit after decimal, and it will again stop because it is a rational number. Now when you solve the third part, then it will matches till the 6 digit after decimal. It will again stop because it is a rational number. So now let's see. So you can see by solving 2 or 3 parts, you are suddenly approaching the exact value of pi, means till 6 digits, which means very fastly you are approaching the pi. Therefore it is called as less irrational number. But why this is approaching the exact value of pi in sudden steps, 2 or 3 parts solving only? So the answer is, it has in every parts very larger numbers. So very larger numbers, therefore a very larger gap, and approaches the pi approximation very fastly. Now when you do the same thing with the golden ratio, phi, the extreme mean ratio, then initially you get, by solving first part 2, then second part, by solving second part you get 1.5, not approaching to phi. Yes, it is 1. And then by solving the third part, you again get 1.6, means you are not moving fastly. So therefore the closer to the phi, the golden ratio approximation will become very tougher. You have to need to solve many and many more fractions, many and many more parts like that, to get the value near about the golden ratio. But why it is slowly approaches the golden ratio? Because these are small numbers, because every part you get smaller numbers, therefore the smaller gap in every values. Therefore we get many difficulties in approaching the value of golden ratio, and hence it is more irrational number than pi. But the fun fact is that the golden ratio is the most irrational number in the world. Okay, because you can see all the numbers are 1 here, and you can't take negative and tell this is more lower than this, because negative is just the inversion of the positive irrational number. And in the next video, this thing will going to blow your mind. Hopefully you get it, so don't forget to like and subscribe.